Next time your video game character sprints across a 3D map, you aren't just holding down a controller button. You are actually triggering a real-time linear algebra engine. Welcome to the deep dive. Today, our mission is to unpack a presentation on how this specific math builds a digital physics engine from the absolute ground up.
Yeah, and we're translating these concepts using the Feynman technique, so we are stripping away all the confusing textbook equations to focus on clear visual analogies, so like a 12-year-old could understand it. We're looking at how developers construct entire virtual worlds and the actual real-life applications behind those tools.
Okay, let's unpack this. Because to build a digital universe, the engine first needs to understand the concept of movement, right? And that starts with vectors.
Right, vectors, which forget the idea of a vector as some mysterious mathematical ghost. Think of it as an item in your game inventory.
Oh, like a physical tool.
Exactly. It is a physical arrow dictating a specific movement instruction, like a treasure map saying, take 3 steps forward.
And those arrows are incredibly adaptable because when your character sprints, the game engine is simply scaling up that movement arrow by, well, multiplying it.
Yep, just multiplying it. And if you walk backward, the engine multiplies your forward arrow by a negative number.
Wait, so you can even stack different arrows end to end?
You can, to create what mathematicians call a linear combination.
I mean, that's just like coding combo moves in a fighting game, right?
Yeah.
You chain a basic punch and a kick together to create an entirely new complex attack path?
That is exactly it. But a movement command is completely useless if the engine doesn't know the boundaries of where those arrows can actually take you.
Right. Which brings us to your span.
Yes, span. It defines your reachable universe. Like, if you only have one arrow, it just gives you a single line to pace back and forth on. 2 arrows build a flat plane.
And then 3 arrows finally unlock full 3D space, letting you jump and fly.
Right. It's kind of like mixing paint. If you only have red and blue, your span is purple. No matter how much you mix them, you can never reach, say, a yellow star without a brand new, completely independent color.
Okay, wait. Let me push back here, though. Because in gaming, more movement options usually mean a better engine. Wouldn't it be much faster for the computer if we just, pre-programmed a bunch of diagonal arrows into the engine?
Oh, you mean instead of forcing it to calculate a mix of forward and sideways every single time?
Yeah. Just hoarding more arrows in your inventory? Doesn't that actually give you more freedom?
You'd think so, but doing that would actually crash the system's memory.
Wait, really?
Yeah, because if you stored every possible diagonal path as a unique arrow, you'd be tracking millions of redundant coordinates. That's a trap called linear dependence, hoarding redundant arrows that don't actually unlock any new space.
Ah, I see.
So instead, developers rely on a basis.
So a basis is what the absolute minimum toolkit.
Spot on. It is the exact bare minimum number of independent arrows needed to reach anywhere in your space with 0 redundancies.
Oh, so just X, Y, and Z.
Yep. By relying only on a basis, the engine computes every possible location using just those 3 numbers. It maps out massive 3D environments without burning through your computer's RAM.
Okay, so we have a highly efficient toolkit generating the boundaries of our world. But games aren't just empty cubes. We have to navigate tricky terrain, like running up a steep ramp.
Right, which introduces the navigation problem.
Because you know how far you move diagonally up that ramp, but how much horizontal ground did you actually cover beneath you?
Exactly. And physics engines solve this using projections. The presentation actually uses a brilliant visual for this.
Oh, the flashlight trick.
Yeah. If you walk up a steep ramp, stop, and shine a flashlight straight down from your current position, the shadow cast perfectly flat onto the floor below is your projection.
So it basically extracts just the forward horizontal part of your diagonal journey.
Precisely. And the real-world application here is spatial tracking. Projections allow the physics engine to accurately track your flat grid coordinates on a 2D minimap.
So is this shadow math how a game figures out where to place my character's icon, even if I'm, mid-air or flying?
That's exactly how. The math forces the spatial data to project perpendicularly downward, completely ignoring your vertical leap to track your true progress.
Wow. So we really are just looking at a workshop of physical tools. Arrows to move, spans to set the boundaries, a flawless basis to save memory, and shadow math to track our location.
If we connect this to the bigger picture, you aren't just learning equations today. You are looking at the literal mechanics of how a digital reality is coded from absolute scratch.
Right, you're understanding the architectural tools of virtual world building.
Totally. It's really fascinating when you break it down like that.
It really is. Which leaves you with one final thing to think about. If a handful of simple, independent mathematical errors are all it takes to perfectly code and simulate our most complex, immersive 3D digital realities, what invisible arrows might be quietly running the physical universe you are sitting in right now? Until next time.